Welcome all of you. Since last couple of classes we discussed varieties of topics, especially recently about evolution of the chemical sheet, pulse phase, receiver phase, evolution of chemical sheet, evolution of coupling constants, how it evolves on resonance or off resonance conditions, all those things we discussed a lot. And then afterwards we also discussed some advanced topics like coherence pathway selection. What is a coherence order? How do you do the phase cycling? By selecting a particular coherence pathway. So these were all very, very important. We can select a particular coherence pathway by using phase cycling. We took number of examples and understood what is phase cycling. And then the same thing can also be done by what is called gradients, pulse field gradients. We discussed a lot about what is pulse field gradient, how we can dephase the signal by gradients, by applying gradients, how what happened to the nuclear spins, precision of the nuclear spin when you apply gradient from the center of the coil above, upper half and lower half, precision in the one is faster, other is slower. We also know by applying strong gradient of then we will ensure that slice thickness becomes narrow and narrow. Finally, it so happens there is a continuous distribution like thing. The spins over the entire sample volume will experience different Larmor frequencies all through. You will get complete dephasing, you don't get any signal at all. We also understood, but dephased signal can also be rephased. A number of applications we understood. We can use the gradients to select a particular coherence pathway of my choice in the homonuclear case and also in the heteronuclear case. Only thing is we need to calculate what is the phase acquired along the Z gradient because of the G1 and G2 in the case of the homonuclear case, which depends upon the pathway you chose, the coherent order you have chosen. If the coherent order chosen before the application of a pulse is P1 and the other is P2, based on this we can find out the phase acquired, and this total phase acquired by both the gradients should be equal to 0 for a refocusing condition. Use that and you can find out the gradient ratio. Same thing you can do for the heteronuclear case. In the case of heteronuclear, now there are two things which you have to understand. If there are gradients G1 and G2, then depending upon how the phase is acquired by both I spin and S spin during G1 and also by phase acquired by I spin S spin during G2, we have to consider, and then find out what is the total phase acquired, and you apply the refocusing condition, get the G1 G2 ratios. You can select the particular pathway. We also understood how we can utilize the gradients for various other applications, including 180-degree pulse imperfections, pulse gradient as a homofoils to remove the transverse magnetization, for a clean selective excitation, for a cleaner selective inversion, all those things we understood. Okay. So I think you have got a hang of some of these topics which will be quite handy when you are designing the NMR experiments. Next we will go into another topic which is used to obtain the information towards the dynamics of the molecules. For example, if you get the NMR parameter like chemical shift, coupling constant, the dipolar couplings, all those things, they give information about the static information of the molecule like molecule structure and conformation. But if I want to get the dynamic information of the molecule, whether what is the motion going on, if molecule is undergoing some motion, etc., I can use another parameter called relaxation parameter. I can find out what is the relaxation, which gives me some more information about dynamics of the molecules. So there is something very interesting thing, another important parameter in NMR, which also is useful in various applications. So we will try to understand what is this relaxation phenomena, how we can measure them. So we will start with a simple thing like this. First, in all the experiments, 1D experiment we have observed, we perturb the equilibrium magnetization where the spins are distributed equally in equilibrium along Z axis by RF pulse. What is going to happen? When you perturb the spins in equilibrium by RF pulse, then you are going to bring the magnetization to perpendicular axis. Whether x axis or y axis does not matter, that is not an important thing now. So what is going to happen? Instantaneously, as soon as you bring the magnetization to x-axis, there is a phase coherence. Temporarily, there is a statistical phase coherence. All the nuclear spins will be aligned along a particular axis. But then what happens? This phase coherence will get disturbed. After some time, the nuclear spins start undergoing decoherence. And at the same time, they will start go back along z-axis. This is a phenomenon which happens. The spins will get completely dephased here, and then afterwards it will go back. First it was along z-axis where there was no coherence, and then you bring them to coherence here by applying an antipulse. This coherence, as I said, interact with the surroundings, and the spin vector start dephasing and keeps rotating in the xy plane. In the xy plane keeps rotating. Initially, as soon as the magnetization is brought to x-axis, there is a statistical phase coherence instantaneously. You get maximum signal. With time, there is a dephasing going on. The signal intensity along this place keeps coming down. If you have a receiver coil here, you detect less signal. The total signal intensity start decaying in the xy plane. Okay, and you wait for a long time, sufficiently long time. After sufficiently long time, the spins will completely undergo decoherence. There is no coherence at all. That means you will not see any signal in the xy plane. If you put a receiver there, you don't get any signal. Zero signal you are going to get it. Okay, this is what happens. There is complete decoherence and you don't see any signal. Fine. Also, what is going to happen to this? You apply a radio frequency pulse, bring the magnetization from z-axis to xy plane and do the experiment. But then if you want to do the signal averaging, you should have the magnetization back again at z-axis to apply another pulse. Magnetization has to come back whether you want it or not. There is what will happen is the magnetization which was disturbed from equilibrium position, from equilibrium condition, bring it back to non-equilibrium state. Now the spins will go back to thermal equilibrium. Okay, they again interact with the surroundings and then slowly they return to equilibrium condition. So now we have understood two phenomena. One, there is a decoherence in the xy plane. At the same time, when undergoing decoherence, at the same time the magnetization start going back along z-axis. So initial magnetization was M0 initially, that is a Z magnetization. After decoherence, once you bring the magnetization to x-axis, there won't be any magnetization along z-axis. Now because of decoherence, there won't be magnetization in the xy plane, and magnetization starts going back to z-axis. And after some time, two things will happen. There is a complete decoherence in the xy plane, there is no magnetization, and complete recovery of the magnetization to z-axis. These two are two independent phenomena, but happening simultaneously. They are happening simultaneously, but they are two independent phenomena. So these two are referred to as two relaxation phenomena. The decoherence of the magnetization in the xy plane is called T2 relaxation. It is called spin-spin relaxation. And growth along z-axis is called T1 relaxation, called spin lattice relaxation. So the processes that brings the magnetization to the thermal equilibrium is relaxation phenomena. Okay. So relaxation, when the magnetization disturbed, when it goes back to z-axis, you will experience these two phenomena: decoherence in the xy plane and growth along z-axis. Both are simultaneously happening. So with this, what are these phenomena? How it is happening? Okay, it is enough if I say these are the two relaxation phenomena. Magnetization has decayed in the xy plane and it has grown along z-axis. One is a spin-spin relaxation, other is a spin lattice relaxation. Fine. These are the two concepts, but two terms. You have to understand more about how it happens, what is the phenomena of concept of relaxation. So we start with the same way, like assuming that I have a sample which is outside the magnet. I will not put the sample in the NMR magnet. I have taken the sample in the NMR to put it outside. In the absence of the magnetic field, There is no net magnetization in the sample. There is no net magnetization because there is a random distribution. Now I am going to put the sample in a magnetic field. Immediately after I put the sample, what is the population between different energy states? If I consider that as 2 spins, what are the population? I am not waiting even for a millisecond or microsecond. Immediately after putting the sample in a magnetic field, I look at the population difference. Both alpha and beta states have equal population. There is no difference in spin population at all. This situation is what is this condition called? This is a condition called saturation. We have discussed earlier in the previous course. When this, you can make the spin states become get equally populated. This is a condition called saturation. We can do that. So now I have not done anything. Taken the sample and put it inside the magnetic field. Immediately after that, I look at the population. They are equal and there is a saturated condition. So what is the population difference between these two? I call this a alpha state and this is a beta state. Number of spins in the alpha state is called n alpha. Number of the spins in the beta state, I call it as n beta. Now what is the difference in the population? Delta P is 0. Remember this delta P is, don't get confused with the previous one where I was talking about difference phase coherence. No, selection of the coherence path, that is different. This is population difference I am talking about. Delta P is equal to 0. Okay. Wait for some time. Don't do anything. Put the sample. Immediately there is no magnetization. There is saturation condition. Population difference is 0. Then wait without doing anything for some time. Slowly the spin starts polarizing along the magnetic field direction. It come back to z axis. Automatically gets polarized. In polarized in such a way, it generates population difference between alpha and beta states. Now you see there are more spins in the direction of the field than opposing it. This is what we discussed. This is because of the Boltzmann population. We know that. So there is a time required for spins to attain thermal equilibrium. When it attains thermal equilibrium, you see the more spins are there in the direction of the field than opposing it. So population difference has been obtained. It takes some time. Now how does the population difference occur? How the spins from here to went there, how the spins from here came down. Now we will discuss two things. I will consider W alpha beta and W beta alpha are the two transition probabilities of the transition from spin alpha to beta and beta to alpha. Alpha to beta upward transition from here to here I will consider as W alpha beta, and spins coming from here to here I consider as W beta alpha. It is a downward. Okay. It is some simple basic conceptual understanding. Of course, there is advanced theory of understanding for relaxation and everything for the benefit of the participants here. That is not essential, but only understand the concept here. Now when this situation will happen, when there is a maximum population here in the alpha state, population difference will become more when beta to alpha becomes more, right? When W beta alpha, the transition probability from beta state to alpha states becomes larger than alpha beta state. Spins can simultaneously go from alpha to beta, beta to alpha. But when this transition probability is larger, there are more spins in the alpha state. That is, more spins aligned along the z axis. Then only system will develop net polarization. That is important consideration. So this is the condition required for the spins to develop net polarization, net magnetization, what you call. When the sample reaches thermal equilibrium, wait for some time. The time is of the order of seconds to millisecond depending upon the sample. It attains thermal equilibrium. Afterwards, no change in the population at all. There won't be any change. The number of population difference when it is attained, it remains same. And that population difference you can calculate after some time, that correspond to what is called Boltzmann distribution formula, which we calculated long back. So it takes some time. All I said is don't do anything. Take the sample, put it in a magnetic field, wait for some time. Instantaneously there is a saturation situation. where the population difference is not there. But after some time there is the develops population. Possibility it can happen because there is more spin, probability of spin coming from beta to alpha is much more than alpha to beta. If that can happen, there is a net polarization. That is what I am telling you. And after some time there won't be any change, it remains same. We will understand this phenomena mathematically in a very elementary basic mathematics, very elementary this thing. And I am not talking about advanced theories of this relaxation. One of the assumption I do, some of the assumption, one, the rate of transition from alpha to beta is proportional to population of the state alpha. If there are more spins, the rate will become more. The rate of transition from alpha to beta, that is W alpha beta, is proportional to N alpha. Okay, rate of transition. Similarly, the first order process is with the rate constant W. It is a first order process. The rate constant is W. The rate of change of population from alpha to beta, from alpha state, is W alpha beta. Change of population from alpha shift has to go to beta. That I consider as rate as alpha beta. Similarly, the rate of population change from beta, I will call it as beta alpha. From beta it has to go to alpha. From alpha state, population has to go to beta. I consider as W alpha beta. From beta it has to come to alpha. I consider as W beta alpha. Okay. Now, if I consider the number, there is a possibility that there is simultaneously everything is going on. From the alpha states to beta state, the spins are going up from alpha to beta. Spins are also coming down from beta to alpha, both are happening. Now, let's from alpha to beta, W alpha beta is there. From here it is going, the probability of spins going from here to alpha to beta, W alpha beta, I will call it negative. I call it as minus alpha beta. Why? Because I am losing the spins from alpha to beta. It is going out. So I call it negative. Now another thing what is happening is, the spins are also coming from beta to alpha. There I am adding up. There is incoming population. Spins are coming back, coming to alpha state. That I call it as plus. So the total change of population of this spin state alpha, if I consider how much population change is going on, some are going up, going out, some are coming in. So this is considered as alpha is equal to minus W alpha beta plus W beta alpha. This is going out, this is a loss, this is a gain. That is what is happening. Okay. And now consider a situation like this. Spins going from alpha to beta is W alpha beta, this is W beta alpha. Now I can find out what is the, from the rate equation, what is the rate of change of this population. This is a simple differential equation. I can do that. I can find out. Okay. Then number of change of number of spins in the alpha state can be given by the simple equation dn alpha by dt is equal to n beta. N beta is the number of spins in the beta state minus the probability of beta to alpha into this one and minus n alpha multiplied by alpha beta. This is the probability. The rate equation for this is what the rate equation for alpha state. Same thing for the rate equation for beta. It goes in the reverse way. Negative for this and positive for this. Okay. Here in the previous example, n beta W beta alpha minus n alpha W alpha beta. But here minus n beta plus n alpha. Okay. That is what is the only thing happening. Because in both the case, one case there is a gain, other case is the other time is a loss. Same thing happens for the beta state also. So this is the rate of change of population for both the spin states. Now when you are at thermal equilibrium, I told you after some time, put the sample in a magnetic field, keep quiet, don't do anything. There is a thermal equilibrium, meaning there is no change in the populations. That means dn alpha by dt should be equal to 0. With time there is no change. So in my condition I have to put this as 0. Correct? This is what the rate of change of population taking the probability into account. That is what I worked out. Simple equation I wrote, phenomenological equations. Now this implies I will make sure n alpha, then if I understand this, then it implies to me n alpha should be equal to n beta. Correct? This is the from this equation you can understand. So that means there is no net gain in the population at all. It is not understandable. We know there is a net population along the z-axis, there is equilibrium population that we are detecting always in NMR. But according to this equation, n alpha is equal to n beta, there is a saturation state after some time. So this is incorrect. So it says there is there is a population difference. According to this, there is no population difference. It is wrong. So my assumption is wrong. Something is wrong in my equation or my understanding. So what we do is, how do you overcome this situation? Instead of replacing the population difference, what we do is we find out deviation from the population from equilibrium. We don't call it as a population difference. Deviation of the population from its equilibrium value. Equilibrium value is n alpha minus n alpha 0. N alpha 0 is the population at the equilibrium state, and then if you similarly if you consider for a beta state, it is n beta minus n beta 0. That is n beta is 0 is the population in the beta state in equilibrium. Okay. So now deviation of this population from the equilibrium if you consider, let us see what happens. We don't consider population difference, we consider the deviation of the population from the equilibrium. You then simple, instead of n alpha and n beta which we were using earlier, put the deviation now, not n alpha or n beta minus n beta 0, n alpha minus n alpha 0 for n alpha. For n beta, dn by d beta or dt, same thing, you have to work it out. This becomes negative, this becomes positive. That we saw earlier. Similarly for the beta state, it is like this. Now this is negative, this becomes positive. Both equations we have written. Are we right now? Let us work out. Using these two equations, the change of z magnetization with time, we can work it out. We will work out. Let us see what happens. We work out what is dmz by dt. dmz by dt is nothing but d of n alpha minus n beta by dt, the change in the population between two states. Now this you can expand it like this. It can be dn alpha by dt minus dn beta by dt. There is no doubt about it. It is very simple. What I did is equilibrium magnetization took, that is the difference of the spin population, and then the change of z magnetization I considered, and then what is the rate of change we found out of mz, we substituted this and just expanded this. Now we know what is dn alpha by dt, we worked out here. What is dnb by dt, we know. Substitute those things here, okay, and do some jugglery, in the sense rearrange the terms. Don't have to, this is a simple high school arithmetic, you do that. Then this is what you are going to get. Minus 2 mz minus m naught into w alpha beta. Now what is mz0? mz0 we have called it as n alpha 0 minus n beta 0. It is the equilibrium magnetization. Difference between alpha and beta states in equilibrium. There is a net magnetization. That should be non-zero. There should be m0 in the equilibrium. So that is there. That I call m0 as n alpha 0 minus n beta 0. Fine. Now if you put it here, dmz by dt, it turns out to be this. Now I have put T1 as a rate constant. I have put T1 from this equation. Instead of this, I am going to put this T1 as a rate constant. So what does this equation tell you now? It is a simple arithmetic we did and arrived at the equations. What does it say? The rate of change of mz is proportional to the deviation from the equilibrium magnetization mz0. What is the deviation? Deviation of mz from its equilibrium magnetization is what you are going to see. The rate of change of mz is the deviation of mz from its equilibrium value. Now if mz equal to m0, the state is at equilibrium. We are attained a thermal equilibrium. What will happen? If you put mz equal to m0, nothing will happen. So mz deviates from m0, but there will be a change of mz. Okay, if mz equal to m0 here, no change. The equation is 0. If mz deviates from m0, not equal to m0, mz is not equal to mz0, if there is a change, then rate of population also deviates. It tells me the rate of population the rate equation tells me the proportion of the deviation of mz from mz0. Or in other words, simple terms, remember, if mz deviates from m0, there will be a change of mz, and this rate of change will be proportional to the deviation of mz from m0. Earlier was different. When the mz0 equal to mz, there is no change, but mz, when it deviates from mz0, there will be a change of mz, and this rate will be proportional to the deviation of mz from mz0. This is what you should understand. Further, the change is written to mz, that is to its equilibrium value mz0. Okay. So, now dmz by dt, if it is like this, you can integrate this equation. Okay, very simple. When I integrate this equation, this turns out to be this thing. I take logarithm of this, simple calculus you can do. Then it turns out to minus t1 by t into t1 by t plus constant. Rearrange the terms. Simple equation I did. This is all high school mathematics you do. mzt now is equal to mz0 minus mz the time t equal to 0, and then exponential t minus t1 in t1 t plus mz0. Some that equation you work out. The thermal equilibrium of magnetization is achieved by an exponential growth function. Okay, the thermal equilibrium is achieved not simply by, it is a linear function. It is obtained by exponentially growth function, because 1 minus something is there. Okay. So, mzt as a function of time, if you calculate, mzd turns out to be m0 into 1 minus exponential minus t by t1. So, there is a growth function. Okay. So, this time constant of exponential t1 is called spin lattice relaxation. The time constant here in this equation, which is the time required for the spins to grow along z axis, is called spin lattice relaxation. So, T1 relaxation is a process by which the net magnetization M returns to its initial maximum value. What is that initial maximum value? M0. That is the thermal equilibrium value. So, the net magnetization M will come back to M0 after some time. That time is called T1. It is the relaxation time. This results in growth of magnetization along z axis. You simply understand what we did is a simple equation. We did this and rearranged something. We got exponential minus t1 by t. Okay, it should be t by t1. There is a mistake here. Okay, some mistake was there. Fine. So, this is what we are going to get, that finally this expression is correct. Remember, this is mz equal to m0 into 1 minus e to the power of t by t1. This is the equation which which tells me about thermal equilibrium of magnetization achieved by an exponential growth. Okay, and this is the T1 relaxation process, which causes the net magnetization to return to initial maximum value, and this phenomenon is called spin lattice relaxation, and the time required for the spin to attain this thermal equilibrium is called spin lattice relaxation time. It is also called T1. It is also called longitudinal relaxation time. It is also called longitudinal relaxation, growth of magnetization along z axis, spin lattice relaxation, attaining thermal equilibrium. All these are the terminologies that normally used. But remember, T1 is a relaxation time. It is spin lattice relaxation time. This process can be diagrammatically given like this. Initially, the magnetization is brought to x axis. Of course, I am not showing the decoherence, which also decoherence is simultaneously going on. Don't ever be under the impression there is no decoherence. The decoherence is shown here by the reduction in the signal intensity. In principle, I should have written all the vectors here. Since it was too much of a work, I didn't do. But I am showing the total magnetization because of decoherence is coming down here in the x axis. So, initially full magnetization, instantaneously there is a phase coherence, and then there is no magnetization along z axis. With the time, this start dephasing here, this intensity comes down, this goes up. See red coming down, blue is going up. Finally red becomes 0, there is a complete blue. Entire magnetization will come back. This is the way the magnetization attains thermal equilibrium. It decays in the xy plane and grows along z axis as a function of time. Okay. And synonyms for this are T1 relaxation, longitudinal relaxation, thermal relaxation, and spin lattice relaxation. These are the terminologies which are used, various things. Okay, so now more about these things we can discuss. Now the time is up. I just wanted to tell you today about what is spin lattice relaxation. Please remember relaxation phenomena. From phenomenologically we will try to work out what is the growth factor, and we know it is the exponential function which is responsible for attaining the thermal equilibrium, and diagrammatically we know what happens. The equilibrium magnetization, when it is disturbed, brought to x axis or y axis, it takes some time, start decohering, and decoherence starts in the xy plane, slowly it will go along z axis. After some time the complete magnetization will be there is a decoherence along x axis, xy plane, and then magnetization completely grow along z axis, and this phenomena is called spin lattice relaxation time. There is a lot more to understand about this phenomena. We will come back and discuss in the next class. So I am going to stop here. Today we have understood more about the relaxation phenomena. Starting with the phenomenological equation, we try to understand a lot of things. What is relaxation? What is minimum? What are the transition probabilities? Why if do not take into account deviation from equilibrium, it does not help us. So finally there must be a net magnetization developed in thermal equilibrium according to Boltzmann population. So all these phenomena conceptually we are trying to understand. We will continue further understanding from next class. Thank you.